Up until now, we've only been differentiating functions that are completely in terms of y. These are called explicit functions, meaning that y is all by itself because it's explicitly expressed in y in terms of x. Okay, so when y is all by itself, it is called an explicit function. An implicit function would be something like the circle function. And we can't get y completely by itself, right? Because we tried this at the beginning of the semester, and we would try to like take the square root of y, but then you have two different functions. So truly, we can't get y all by itself in a function like this. These are all considered implicit functions, okay? And when we do differentiation for an implicit function, it's a little different than when we do it for an explicit function. If you think about it, y is a function of x. So imagine I had x, y squared equals 2, okay? Y is just some function of x. It could be any function of x, right? It could be 2x. It could be square root of x plus 3 to the 1/3, which doesn't make any sense, to the 7th. It could be any function of x, right? It could be anything inside of that y, because, you know, it could be y equals and then anything with an x, right? So how do we take the derivative of this, imagining that y is a function of x? So there's something inside there with a bunch of x's, you know, like let's just say 3x plus 5. Let's just say that's a function. We don't know, but how would we take the derivative of this? Well, you know, we would take the derivative of the x, you know, we would do the fig plus gif, okay? And we would take the derivative of, let's see, derivative of f, which is 1, times 3x plus 5 squared, plus the derivative of the second function. And how do we take the derivative of the second function? Well, we take the derivative of the outside function, right, which would be 2 times the inside function. And then we tack on the derivative of the inside function, or 3. So now, what if I don't actually know what the inside function is? What if this is just some function of x, like y? Well, anywhere that I had 3x plus 5, I'm just going to have y, right? And then I had the derivative of that inside function, which was 3 for that inside function, but we don't actually know what the derivative of this inside function is. So I can write it as just y prime. Oh, what? I can? Yes, you can. So the derivative of y squared with respect to x would be 2y prime, because I took the derivative of the outside function with the inside function still intact, which is the y, times the derivative of the inside function, which is just y prime. Okay, how does this actually work with real functions? Our procedure is that we differentiate both sides with respect to x. Remember, that means that is our independent variable. X is the variable that we're talking about. So we differentiate both sides of the equation with respect to x. Then we get all the y primes, or dy dx's, on one side. We factor out the y primes, and then we divide so that y prime gets completely alone. So in the end, your implicit differentiation answer is going to have y prime completely alone, just like all of our other ones. It's just going to take a little bit of work. Okay, so let's differentiate this. Well, if I wanted to just differentiate it the way we were before, you're thinking like, oh, well, duh, that's just y prime equals 1, right? Yeah, well, what if we did it with implicit differentiation? Okay, so we derive the left side, which is, you know, dy dx, or y prime, and we differentiate the right side, which is 1. And then I get all the dy dx's on the same side. They are, and I'm done. Do you see how implicit differentiation isn't that different from what we've been doing? It's just that sometimes the y's aren't by themselves. So let's do this one. The derivative of this side is y prime, and the derivative of that side is 2x. Are all the y primes on the same side? Yep. Are they alone? Yep. So we're done. Let's differentiate this one. Y prime equals, now this is a chain rule. I know, so cheesy. All right, so I bring the 2 down, I eat the outside, and I leave the inside still intact. Then I eat the inside. So I end up with y prime being 4 times 2x minus 1. I could simplify that by distributing, but I don't have to. All right. What about this? Okay, well this is literally what I just did, isn't it? This is the exact same function. The only difference is this time I don't know what's inside, right? So how do I differentiate it? Well, I take the derivative of the outside function with the inside function still intact. So f of x didn't change at all. And then I take the derivative of the inside function, which is f prime of x. That's it. That's the whole derivative. Let's go to the next one. I was going to say something, but the next one actually goes over it. I didn't think of that. Okay, let's derive both sides. Derivative of x with respect to x is 1. Now y is a function of x, right? So my outside function is some function of x squared. Okay, so I'm just going to actually rewrite my function here instead of differentiating first. So this is some function of x that we don't know, but it's a function of x, right? Because y is any function of x. Now I'm going to derive, so I can do the derivative of x with respect to x is just 1. Now I take the derivative of the outside. I leave the inside still intact, so it's just y. Right? And then I take the derivative of the inside, which is y prime. Now with something like this, this is where I need to get all those y primes completely alone, okay? So we'll show you in the next one, but really y prime needs to be all by itself, so we're just going to divide both sides by 2y, and you get y prime equals 1 over 2y. All right, let's try some harder ones. Given this function, find y prime. Now this is an implicit function because y cannot be taken and made by itself. So we're just going to take the derivative of both sides. Both sides. See, we're not used to taking the derivative of both sides because when we take the derivative of y, it just becomes dy dx. But we're going to take the derivative of both sides. So here we have 2x squared x squared becomes 2x. Then to differentiate this, I take the derivative of the outside with the, that should be squared, with the inside still intact, and then I take the derivative of the inside, which is just y prime. Remember, it's just a hook-on, really, plus the derivative of 3x is 3, and the derivative of 6 is 0. So now I can simplify this out. So this is 2x minus 6, y squared y prime plus 3 equals 0. Now I need to get y prime all by itself because I was finding, it says find y prime. You can't just be like, oh look, there it is. You have to have it by itself. So we're going to subtract 2x over, and I have negative 6y squared y prime plus 3 equals negative 2x. Minus 3x, negative 6y squared y prime equals negative 2x minus 3. And then to get y prime by itself, I needed to divide both sides by negative 6y squared. Hopefully that will, come on, work. It just disconnected. Hang on, I guess I'll pause it for a minute to get it to connect again. All right, there we go, I got it working. So we divide both sides by negative 6y squared, and I end up with y prime equals negative 2x minus 3 over negative 6y squared. That is the derivative at any given point on this function. So it's the slope of the tangent line at any point. So the next thing says, find the slope of the tangent to and normal to the graph of this function. Okay, so this is an ellipse, and it's asking us to find the tangent and the normal slopes, not the equations, just the slope. So all I have to do is find the slope, which really is just the derivative at a point. Okay, so I take the derivative of both sides. So I take the derivative of 2x, x squared, which is 2x. I take the derivative of 4y squared, which is just like I take the derivative of it, right? And then I just tack on y prime. That's really all I have to do. That's where that chain rule thing. And then derivative of 25 is 0. And then I need to get y prime by itself. So I have 8y, y prime equals negative 2x. Divide by 8y, divide by 8y. And I'm going to have that y prime equals negative 2x over 8y. So this tells us the derivative at any point on the graph. And now I need to find the actual value of that derivative at any point on the graph, okay? So what is the slope of the tangent line at the point 3, 2? Well, look, here's an x value. And looky there, there's an x. And here's a y value, and look there, there's a y. So why don't I just plug those in? So y prime at 3, 2 equals negative 2 times 3 over 8 times 2. So y prime equals negative 6 over 16, which is negative 3/8. So the slope of the tangent line equals negative 3/8. That's what it asked for. But then it also asked for the slope of the normal line. And remember, the slope of the normal line is just the opposite reciprocal because it's a perpendicular line. So it would be 8/3.